Today we're going to be looking at a topic called difference of squares. And when you're looking at this, you're probably thinking, uh, this isn't written in simplified form. So you're right, these are already factored versions. But we want to take a look at some patterns that are established before we get into today's lesson. So this is a warm-up just to kind of get us thinking in the right way. If I were trying to multiply these two groups together, I would either have to use the visual method, the area model, or I might just recognize this is distributive property a couple of times. So if I'm over here, I could say distribute this x to both places, distribute this 3 to both places, and essentially I'm going to have 4 products. Now, if you're a visual person, because I'm a visual person, we also had talked about the area model where you say, this is a binomial, so I'm going to put out both of its parts in a rectangle. This is a binomial, I'm going to put both of its parts in the rectangle. And now, visually, you can see that you're supposed to get 4 products. So you get your 4 products. 3 times x is 3x. 3 times negative 3 is negative 9. But instead of getting 4 answers listed down here, I only have x squared once. These are both x to the first power, so they're like terms, and you end up combining them. But 3x minus 3x, that's gone. That's 0x. Now, I don't have to write 0x on here. It's kind of a waste because 0 times anything is 0. So mathematicians aren't going to spend time writing that 0x. They're just going to skip it and give the audience what they need to know, which is what actually exists. X squared minus 9. Notice there's only 2 terms there. I got 4 products, but it resulted in just 2 terms. If you're a person that just loves algebra and you're very comfortable, you don't have to do out that box. I like to see my 4 products. You could have done it straight out of this. X times x is x squared. X times negative 3 is negative 3x. 3 times x is 3x. 3 times negative 3 is negative 9. You can still get those 4 products with distributive property. Even if I make it more complicated, I'm still doing exactly the same process. I'm still getting my 4 products, just like I was before. Again, I'll do the area model just because it's a good visual way to see what's happening. It's a binomial times a binomial, so I'm going to have a 2 by 2 box. So I'm just setting up my 2 by 2 box. I have to have a way to show this minus in between, so I'm treating it as a negative when I do my multiplications. Now I've got 2 times 2 is 4. Add the exponents. 2 times 5 is 10. The x is still there. Negative 5 times 2x is negative 10x. Negative 5 times 5 is 25. Oh, I almost made a mistake. Got to be careful with those signages. But again, I have this same exact pattern. Notice in the other example, I'll shift to the side here. In the other example, my x's canceled out. In this example, the same exact thing happened with the x. The 4x squared is all by itself. There is only one multiplication that netted an x squared. But the x's, negative 10 plus 10, turned into 0x. So I don't have x again, and I have minus 25. So you can see in both of the examples we started with, I ended up with only 2 items in my list. I got a binomial for an answer. I got a binomial for an answer. That's not typical. When we did all of these, that unit that we did this in, we got a law of trinomials because you had to add these together and usually you ended up with something. So it must be that there's a special way this is set up. So if we go back and look at this, we say, oh, those front numbers were identical. X, X, those were the same. But the back, the only difference was that one of them was a positive and the other was a negative. Positive 3, negative 3. Even on this one, negative 5, positive 5. It doesn't matter what order they were in. What matters is that one was a positive, one was a negative in the middle. Notice these were both 2x in front. So we're going to do something now. I'm going to erase this, and we're going to talk about how do you do a difference of square problem. And now we're ready for a difference of square. Let's say I did x squared minus 16. Let's say I upped it and did 9x to the fourth minus 25. So I've got two problems that I want to start kind of fresh on. And now I'm going to give you the true directions. What you're going to be seeing is this. Factor completely. So now it's time to go, what am I supposed to factor by? Because you'll remember when we were doing greatest common factor, we were looking for what's the same in every place. Well, there's nothing the same in every place. This has an x and this doesn't. This coefficient is 1. I can't pull anything out if it's just a 1. So the temptation here is to say there's nothing that I can do. But when we look and see that it's a binomial, we now have to ask ourselves, okay, is it possible that both of these are perfect squares? Because if they're both perfect squares, then there is something special we can do. So what do I mean by a perfect square? Well, you'll remember any number times itself, like 3 times 3 is 9, 5 times 5 is 25. These are perfect squares. So as long as I could get the same number, if I made one of them a plus and the other one a minus, when I go to add them together in that same way I did before, they're going to cancel out. But I have to be able to make perfect squares in order for this to work. That's why we call these difference of squares problem, because both numbers have to be a perfect square. So when I look at this and say, how could I get x squared with the same factor? I could do it if I did x times x. So my answers when I'm doing this type of factoring, when the directions say factor completely, and I'm starting to think, okay, this is going to be one of those odd kind of grouping problems. The front is made up of x times x, so I'm going to put those two numbers here and here. Remember, when I do distributive property at the end, it's going to show that we get these things back. Now I look at the 16. I have to say, what made 16 happen? This is the end product, but I want to know what created that end product. Kind of like the reverse engineering model. You see an exhaust pipe, you know that it had to come off from something so you could follow the exhaust pipe back. I see a 16, I know that 16 had to come from something. So I'm thinking, what two numbers can I multiply together that's going to give me 16 as an answer? And if I check, I get 4 times 4. 4 times 4 will give me 16. So if the front can be created with x times x, the last number, the back number, can be created with 4 times 4. Now we just need to make it a difference of squares. Because I don't have anything in the middle here, it's only a binomial, not a trinomial. I know that one of these had to be a plus and the other had to be a minus. Out of simplicity, I want to try to establish a pattern. As you move into Algebra 2, there are some things coming up a little later. It doesn't matter what order you write these in. I typically write my negative first. It's just preference. There's no reason that you would have to do that. I'm just establishing this. If any of you have me for Algebra 2, we're going to be revisiting a deeper version of this stuff, and I like to write my difference first. So there it is. We have a difference of squares. Because both of these numbers were perfect squares, I was able to write an answer. Same thing when I come over to here. When I see there's just 2 terms and there's nothing common, x can't come out of both of these. I can't divide anything out of both of those numbers. Now I need to check and see, are they both perfect squares? Because if they're both perfect squares, I can do it. So I look at 9, and I know 3 is the only thing that goes into it, but I have x to the 4th this time. So now I've got to think, okay, x to the 4th is like this. If I were to split that up into x squared and x squared, then I would have x to the 4th when I multiplied them all together. So 9 is a perfect square. It comes from 3. X to the 4th comes from x squared. So I had a more complicated looking front number, but if you multiply these two together, I get my 9 and I get my x to the 4th. So I can see that this was a perfect square. It was 3x squared times 3x squared. Because it's the front number, I'm going to write that in the front. Now I look at my back number. I'm supposed to be getting 25 here. In order to get 25, I have to have 5 and 5. 5 times 5 is 25. So I know that I'm going to need a 5 and a 5. The only way this ever works is if it's a difference, because I've got to have one of them being minus and the other being plus. That way, if I were going to do my 4 products, again, this is just checking the work. This is it. This is all you need for the answer. But as a mathematician and showing you the very first time you've seen this, I just want to prove to you that when you multiply this back out, you're going to get back to the original expression that you had. It's a binomial, so I'm going to write each term on the edge. This is a binomial, so I'm going to write each term on the edge. And I can see in my area model as I multiply these, 9x to the 4th, 15x squared, negative 15x squared, negative 25. I see that my two like terms are opposites and they cancel out when I add them. And I'm just left with the 9x to the 4th minus 25. Again, you don't have to do this because the whole point here when it said factor was to write it as a multiplication problem. Now it's written as a multiplication problem. What's different about this from the GCF lessons you were looking at is that now we have a group of things times a group of things. Whereas the GCF problems, you're just pulling out a single common factor. Now I'm pulling out, I have a group of common factors, common, because it's unusual to think of these as common factors until you understand difference of squares. Both of these have to be squares in order to do the process. So maybe this was a little harder than it needed to be, but I wanted to show you the full scope of everything you could see in this unit. Most of them are going to look more like this, and you'll quickly start recognizing your perfect squares as you do more of these. So enjoy the work, and thank you for watching.